Problem 14.85 is really problem 14.84, just plugging in numbers to the solution of 14.84. We're given M85 that the width of the stream is 12 feet, that the D1 distance depth here in 1 is 4 feet, and the depth over here at 2 is 2 feet. We're also given, I'm going to look at a little differential area element right here. And we come over and look at this area element. It has a B of width and a dy of extension. We're going to need that in a moment, so that B times dy is the differential area element. We're to find Q. Q is a volume flow rate. It's a volume per unit of time, which technically it's the mass per unit of time divided by the density being mass per unit volume. The masses would cancel out and you'd end up with volume per unit time. And the density can be expressed as the specific weight divided by G, because specific weight is for water 62.4 pounds per foot cubed. We don't need that, but if you divide that by G, which means the G would go up here, you would get so much mass per unit volume. Anyway, this is the relationship between Q and the dm dt that we use, and the specific weight. So what we want to look at down here to calculate the force, the average force at 1, it pushes a delta M of mass into the system right here. And over here you got a force that resists the delta M of mass coming out. The little delta M of mass right here has a length of delta x1, and the little delta M of mass over here has a length of delta x2 there. So the delta M, the volume here, obviously has got the area that you see there times B, the width of the stream. So what we want to look at is the pressure that you have with a depth here, and the pressure increases as you go down. Atmospheric pressure would be a pressure that gets you to the absolute pressure down here, but we're going to ignore that because atmospheric pressure is going to be a constant add-on to this pressure here. It's going to be a constant add-on to this pressure over here that we have, and it's going to subtract away in our equations that we develop later on. So what we're going to do, though, is take a look at pressure. It's a force per unit area, or dF times dA, and the pressure at a certain depth y, where y is measured positively downward, is rho gy. So the further you go down into the fluid, the greater the pressure is. Rho is the density of the water or the fluid that you're involved with. In a separate video, I'm going to show you or remind you how pressure comes about. But anyway, we'll use it right here as rho gy. We'll set up an integral, df equal to double integral, because we're going to write out rho gy and differential area element I'm going to call dy dz, with z being measured in and out of the paper. Okay, and then if you integrate on z first of all, you end up just getting b, which is the width of the stream, and then you're left with the integral of y dy. And when you integrate that, of course, you get y squared over 2. And so the force in general will be 1/2 rho gb y squared, assuming that you're starting at 0 on y and integrating up to y. All right, so that means that F1 then, the force over here, the average force you have on that side, is a 1/2 rho gb d1 squared, and then the force over here on this side is a 1/2 rho gb d2 squared. These diagrams that they show right here really are pressure diagrams. So the pressure at the bottom here is really just going to be rho g d1 d2 here and a rho g d1. And so if you want to get the area, you could talk about B and D2 for the area right there, multiply it times the average pressure, which would be 1/2 of all that, and you'd still end up with these forces that I have down here. All right, the next thing we're going to look at then is setting up this Q, again, as a volume per unit time, because one of the things we've got to do is we've got to get rid of V1 and V2. We've got to get it over in terms of something that is known or something that we're looking for. So remember that this volume per unit time can be written as a delta V divided by delta T. And a delta V of volume right here that we would have would be the area that you're seeing right here, which is a delta X1 times a D1, and then you got a depth of B. So it would be BD1 delta X1 divided by delta T. But delta X1 over delta T is V1. And so similar you would get for the other side in terms of V2, you get a B D2 times V2. And this is information then you're going to need to work the rest of this problem. Continue on with 1485. We're going to look at a delta M of mass entering from the left with a velocity V1. You got your system momenta, then you got your external impulses applied. There's an F1 delta T to the right and a minus F2 delta T to the left from the right, from the left and right sides. And that's going to be equal to your final momentum, which is a delta M exiting with V2 velocity plus your system momenta. System momenta will cancel out on each side. Divide through by delta T and you end up with dm dt times V1 plus then F minus F2 right there, and then the dm dt times V2 over here. The dm dt from the previous page can be written as a specific weight times Q divided by G. The V1 can be written as Q over BD1. The F's are 1/2 rho GB D1 squared and 1/2 rho GB D2 squared. And then again, dm dt is gamma Q over G, and then the V2 is a Q over BD2. And so you can see we're going to end up with Q squared terms. The specific weight's going to cancel out, or excuse me, the specific weight over G is the density, and that's so that's density, this is density, and that's density again, so those all cancel out. So you're left with Q squared. You also can multiply, let's see, okay, the G's are already gone, so we have Q squared then left up here over BD1, and then we have the same thing coming over here, Q squared over BD2, so we bring these over and collect the Q squared terms together right there, and then we take this to the other side and we'll end up with GB over 2 right there, and giving it right here, GB over 2, and then D1 squared, or excuse me, D2 squared minus D1 squared, since we've taken it to the right hand side of the equation. All right, and then notice that this can be factored into D2 minus D1 and D2 plus D1, and then this can be rewritten right here as D2 minus D1 over D1 D2. Well, the D2 minus D1 terms are going to cancel out, and the D1 D2 will be multiplied over times this side. So the B comes over to become a B squared, which after we take the square root is going to come outside and be just B outside. The 1/2 G is going to stay underneath the radical. The D1 D2 are coming from right there, so there's D1 D2. This has been canceled out with that, so that leaves me with D2 plus D1 on the radical, and so when you plug your numbers into that, you'll get 646 foot cubed per second.